Welcome everyone to 11.5 alternating series. Now up until this point, all of our series have been positive, right? So pretty much all of our tests and everything have always required us to have positive terms. But it turns out there's one more type of series that's very natural, especially as we continue up into 11.8 and 9 and stuff like this as we're dealing with something called power series. These alternating series occur quite naturally, and alternating series will go positive, negative, so they'll actually have some negative terms. All right, so we'll define more formally alternating series, and then we'll try to determine, well, when do these things converge and diverge? So let's get to it with a definition.
So, like I mentioned, an alternating series is a series whose terms are alternately positive and negative. So here's an example. We have 1, negative 1/2, plus 1/3, negative 1/4, plus 1/5, negative 1/6, and it goes on forever and ever. So that's the same thing as the sum from n equals 1 to infinity of negative 1 raised to some power. So I'm going to put an n here, but the problem is if I plugged in 1 for n, I would have negative 1 to the first power. So the first term here would be negative 1, but I want it to be positive 1. So in order to get it to be positive, I'm going to do n minus 1. And now you can check if I was to plug in n equals 1, I'd be taking negative 1 to the 0th power, and so that would be positive. Okay, and then times 1 over n. So this is going to give me the 1 over 1, 1 over 2, 1 over 3, 1 over 4, so on and so forth. Okay, so this is a pretty nice and famous alternating series here. So the nth term of an alternating series is of the form an equals negative 1 to the n minus 1 times some bn, or it's of the form an equals negative 1 to the n times bn. So where bn is a positive number, oops, sorry, I forgot my equal sign. There we go. So bn is a positive number. In fact, bn is just the absolute value of an. Okay, now that we have alternating series, we can talk about an alternating series test. So this is a nice named theorem. You're expected to know this. So if you have a nice alternating series and it satisfies two things. So first of all, it needs to be decreasing. So that's to say that b sub n plus 1 is less than or equal to bn. And these are positive things here, right? For all n. And that the limit as n goes to infinity of these b sub n terms is equal to 0, then the series is convergent. Okay, so decreasing and the limit approaches 0. Remember, b sub n is just the absolute value of the a sub n terms in this case. Okay, so let's go ahead and try to apply this thing to the following series. So we have the nice alternating series, negative 1 raised to the n plus 1, which we could think about this as just negative 1 raised to the n minus 1 power times negative 1 raised to the second power. So it'd be the same thing essentially. And then 1 over n times 3 to the n. Okay. So the first thing is I need to show that this is decreasing, right? My b sub n's are decreasing. So maybe I could say that n is an increasing function and 3 to the n is also an increasing function. So if I multiply these things together, I would have n times 3 to the n, which would also be increasing. And so if I took the reciprocal of that, that would be decreasing. All right, so we have decreasing, and in fact, the limit as 1 over n times 3 to the n, well, this will get really close to 0. Right? Because as n gets very large, 1 over n would head towards 0, and same thing, 1 over 3 to the n. This would also head towards 0. So by properties of limits, we know that this will head towards 0. So now, by the alternating series test, we know that our alternating series converges. So that is the series of negative 1 raised to the n plus 1 power times 1 over n times 3 to the n is convergent. All right, so let's try one more here in this video. So in this case, we have the series, let's see, negative 1 to the nth power times n squared over 1 plus e to the 2n. Okay, so I need to show that this is a decreasing function, but the problem is n squared on top is increasing. So this is not, there's some opposing forces here. N squared is trying to increase, and then this 1 plus e to the 2n is trying to, well, also increase, but since it's in the denominator, it's trying to pull this function down. So I'm going to need to take the derivative here. I'm going to have to try to figure out what's going on. So let's consider the function. And we'll take the derivative and try to figure out, is this thing increasing or decreasing? So according to the quotient rule, the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And here's where I have to use my Calc 1 knowledge and try to expand this out, and then we'll try to factor it after that. So let's expand. 2x plus 2x e to the 2x minus 2x squared e to the 2x. Okay, and the denominator stays the exact same. Okay, now at this point we can see there's a 2x in the numerator in each one of these terms, so let's factor out that 2x. And again, the denominator will stay the exact same. And then finally, in two of these terms, I see an e to the 2x. So I'm going to go ahead and try to factor that out of those two terms. So that's going to give me this 1 minus x times e to the 2x. And the denominator's the same. So now let's think about this a little bit. The denominator is certainly going to be positive, right? It's squared. This 2x, that's certainly going to be positive, right? Because x is greater than or equal to 1. And now we have to look at this complicated part. Right, so 1 plus 1 minus x times e to the 2x. Well, e to the 2x is going to be positive, right? So what about this 1 minus x? Well, this 1 minus x is going to be less than 0. And in fact, it's going to be less than, well, not 1, sorry, this is a mistake. It's actually less than negative 1, right? Because I need to add 1 to that, and then it's going to be less than 0 still. So this entire part right here is actually less than 0. So the entire thing is going to be less than 0. And now you do have to be a little bit careful. It's only going to be less than negative 1 when x is actually 2 or bigger. So there's a little bit more of an argument that needs to go into this. But the claim is that this actually is decreasing. Okay, so we have decreasing. The other thing we need to show is, what about this limit, right? So we take the limit of n squared over 1 plus e to the 2n, and I would like to show that this approaches 0. Well, we can apply L'Hopital's rule, right? So these are both heading towards infinity. So L'Hopital's rule says that this should be the same as the limit of 2n divided by, well, this would be like e to the 2n and then times 2. A little bit of cancellation here. And looking at this, well, they both still head towards infinity, so we still have an indeterminate form of infinity over infinity. So L'Hopital's rule again, and now we get 1 divided by, this is going to be e to the 2n and then 2. And now as n gets very large, we can see that this approaches 0. Okay, so therefore, by the alternating series test, right, we've shown that it's decreasing, and we've shown that the limit goes to 0. So by the alternating series test, we know that our series, this negative 1 to the n times n squared over 1 plus e to the 2n, converges. So again, we're showing our work, we're saying what test we're using.
All right, and with that, I think that's probably a good place for us to go ahead and take a break. As you can see, alternating series are a little easier to calculate, do they converge or diverge, but they still do have a hypothesis. We have to make sure to show that they are decreasing. All right, I'll see you next time.